Hey class, here's a video on blackbody radiation and how to use one of the two equations related to blackbody radiation, which is called Wien's law. And these are all examples of objects that emit what's called blackbody radiation. Blackbody radiation is just the light that's emitted from a hot glowing object. So things like the filament of an incandescent light bulb just heats up. That's what produces light. If you use an electric stove or hot plate, it gets hot enough to the point where it starts to glow red. And then the very important example of blackbody radiation is the light that is emitted from stars, which is just due to the fact that they are very hot. Before we get into Wien's law and blackbody radiation, just a quick note about temperature. In astronomy and in most sciences, we exclusively use the Kelvin temperature scale. Read about it in chapter 5 of the book. But the Kelvin scale is very similar to the Celsius scale, but it's offset such that it never goes negative. So there is actually a lowest temperature that an object can achieve, and there's no such thing as a temperature which is lower than that. We call it absolute zero, and that corresponds to 0 on the Kelvin scale, which is negative 273 on the Celsius scale. But we're not going to use Celsius, and you don't even have to worry about converting. We'll always use Kelvin. And looking at this, here's some interesting numbers. Average human body temperature. Normally you think of this as 98 degrees Fahrenheit. So if you get sick, you make sure that your temperature doesn't go too much higher than that. But in Kelvin, body temperature is about 310 Kelvin. And then we're going to be using the Kelvin temperature scale to describe the temperature of stars. So blackbody radiation, when an object, you have a solid object, and if you heat it up, it starts to glow, and it will emit light. So this is out of your textbook, and it will emit light that is described by what's called a spectrum. So for example, if you have an object which is at 6,000 Kelvin, this is pretty close to the temperature of our sun. This curve right here, its spectrum, this tells you how much light it produces at each of these various wavelengths, and this is measured in nanometers. So 500 nanometers is green light, 700 nanometers is red light, and about 400, a little bit less than 400 nanometers is violet light. This is ultraviolet over here, this is infrared. And this curve, this blackbody curve, this tells you if you have an object which is at 6,000 Kelvin, it tells you how much light it's producing at each of the wavelengths. And here is the equation that we're going to learn how to use right now. This is called the Wien's displacement law. And what this does is it relates this wavelength, which we call lambda max. This is the wavelength of maximum emission. It's the wavelength at which the spectrum of an object peaks. And this, measured in meters, so you'd have to convert from nanometers to meters and vice versa. Wien's law tells us that the wavelength at which the spectrum of a glowing object peaks is equal to this number, 0.0029, divided by the temperature of the object in Kelvin. So this has to be in meters, this has to be in Kelvin. And what you notice is that the higher the temperature, the lower the wavelength of maximum emission is. So when you go from a 6,000 Kelvin object to a 7,500 Kelvin object, which would be a hotter star, the wavelength at which it peaks actually shifts to shorter wavelength. As T gets larger, lambda max becomes smaller. And then down here, what I've done, and I will, on the final exam, I'll provide you with both versions of this equation. All I've done is I've cross-multiplied. So I've brought the T up here and the lambda max down here. In this form right here, you can plug the temperature in and calculate what the wavelength of maximum emission is. Here, you can plug what the wavelength of maximum emission is, and you can calculate the temperature based on that. And I'm going to do a quick example of both. So here's the light bulb right here. The old-fashioned incandescent light bulb, it produces light just because this metal filament right here, it heats up when you turn it on, and it starts to glow. Well, light bulbs are designed so that these filaments reach a temperature of about 3000 Kelvin, which is about half the temperature of the surface of the sun. So to calculate the wavelength at which this light bulb is going to produce most of its light, at which its spectrum is going to peak, all you got to do is you take this Kelvin temperature and you plug it into the Wien's displacement law, which I've done right here. So you take the 3000, put it in there for T, and you use your calculator, 0.0029 divided by 3000, and this is what your calculator puts out. And if this is in Kelvin, lambda max is going to come out in meters. So that's the wavelength in meters. Look at this. You move the decimal place 7 spots to the right and then put the decimal place here, so it becomes 9.67. Since I moved the decimal place over 7 spots, this is going to be times 10 to the negative 7 meters. Now, 10 to the negative 7 does not have a special name, so we want to go 2 more spots. And if we go 2 more spots, that means that we'll have moved the decimal place 9 spots to the right, so it becomes 967 times 10 to the minus 9. So keep in mind, these are the same exact number. This is written in decimal, this is written in scientific notation. And 10 to the minus 9 meters has a special name. It's called a nanometer. So there it is, 967 nanometers. You ask the question, what kind of light is this? If the wavelength is 967 nanometers. Well, keep in mind, visible light goes from 400, roughly, violet light, up to 700, red light. So this is even longer than red light. So this is what we call infrared light. And this is what the spectrum of an incandescent light bulb looks like. The spectrum is peaking at, what did we have? We had 967 nanometers. That's right around here, just a little bit less than 1,000 nanometers. This is in the infrared. This is the visible, and that's the ultraviolet. So when you turn on an old-fashioned light bulb, the majority of the energy that you're using to power the light bulb is going into producing infrared light, which normally is not what you want to use the light bulb for. The only visible light is just this part of the spectrum right here. This is what you see with your eyes, but most of the energy is going to producing infrared light. And that's why we are, for the most part, replacing these with compact fluorescent lights, because these are very inefficient. They're producing mainly infrared light. Here's another example of using the Wien's displacement law. You look at the sun, and you take a spectrum of the sun's light. So you measure how bright the sun is at all these different wavelengths in nanometers. And if you look at this spectrum, you identify that the spectrum peaks at 500 nanometers. The spectrum of light from the sun peaks at a wavelength of 500 nanometers. Use this to calculate the temperature of the sun. So in this case, we want to use this version of the Wien's displacement law, where we plug lambda max in and we solve for T. Now we're given lambda max in nanometers. We're told that it's 500 nanometers. You cannot plug that in here because this has to be in meters. This will be in Kelvin. All right. Whenever you're using Wien's law, lambda max is in meters, temperature is in Kelvin. So the first thing we want to do is we want to convert 500 nanometers into meters. Well, nanometer is just 10 to the minus 9 meters. So it's 500 times 10 to the minus 9 meters. And then to put this into decimal, you can move the decimal place 9 spots to the left and you get this right here, 0.000000500 meters. Now that you have the wavelength of maximum emission, lambda max, in meters, now you can just plug it in here, and that's what I've done. So you just take this number. This never changes, 0.0029. That's just part of the equation. This is the observed wavelength of maximum emission of the sun, and you put this in your calculator and you get a temperature of 5,800 Kelvin. That's how we know the temperature of the sun, and you can do this for any other star, and you're going to get some practice doing this in your homework. And so with any other star, all you have to do is measure the spectrum of the star, identify the wavelength at which it peaks. So for example, if it peaks here in the blue-violet, you would take that wavelength of maximum emission, plug it into Wien's law. the Wien's displacement law, and you can get that its temperature is 7,500 Kelvin.